Good morning, everyone. First, thank you all for having me. My name is Stef Houten, and I'm going to talk about leveraging AI to simplify complex configurations. We as developers have been using AI a lot lately, and we wanted to give something to our customers so that they could also leverage this. First, a little bit about me. I've been a software developer for around 5 years. I have most of my experiences with Python, but I also sidetracked into PHP with some Laravel. And I used to be a full stack developer, but I don't really enjoy doing front end as much. So I really enjoy working on the back end. So some of the interesting projects I've worked on during COVID, I did something for the Corona Melder. Also have some experience with planning software for hospitals, for example, for the Erasmus ziekenhuis. Been involved in some warehousing software, and I also worked on real-time systems for amusement parks. And currently at Eventim, I've had some really interesting projects. I got to migrate a reporting service from a sync service to an asynchronous one, which allowed us to introduce streaming to get rid of some memory issues we were running into. And I also worked on the queue for our shops, which has recently gotten a lot of traffic with some very popular sales. So we could get rid of some scaling issues we were having there. And my most recent project I'm working on is the AI assistant, which I'm giving a talk about now. And what drives me as a developer is I really like working with projects that have a lot of skill and performance issues. So that's perfect for where I'm working now. A little bit about Eventim. Eventim is Europe's largest ticketing and live entertainment platform. So we sell a lot of tickets, and we sell them for concerts, festivals, sports, and theater events. And we also have a back office to configure these events. And in this back office, you can also monitor sales, and we have reporting there. So some technical challenges we are running into. We have a lot of traffic spikes because we sell events, tickets for events, which means we have massive loads during popular releases. This means we must build scalable software. And we also have a very large code base. This means we're having a lot of different services, and deployment is complex. Sorry, I don't know what's going on. So the deployment is very complex, and we have a lot of legacy code. Yeah, I don't know what's going on. I'm sorry. Ja, ik weet niet. Moet je hem een beetje. Gewoon lekker rustig aan en dan als ik iets voor je kan doen, moet je zeggen. Een glasje water. Ja. Yeah, so we have a very large code base with a lot of different services, which also means that deployment is complex. And we also have a lot of legacy code, which makes it hard to work with. We also have a lot of event configuration and features for specific customers, which means we have a lot of configuration flows. That makes it really complex to set up an event. Sometimes you just want to publish something and you need to do like 4 or 5 additional checks before you can get that done. And because we sell so many tickets and we have so many events, we also have a very large reports. So we have hundreds of millions of rows, which means we have to also write scalable queries. And we're currently running into some issues where we're having some timeouts. And these reports, because they're so large, we sometimes run into memory issues, which means one single worker can use up to 500 megabytes of RAM for that specific report. So what we'll cover in this presentation today is how this project started, how we're leveraging existing infrastructure, how we can use natural language workflows, some controlled API execution, security and operational guardrails, and some lessons I've learned. So this project started with a manager who did this as a hobby project. He didn't get to coding a lot anymore, so he did this in the weekend. And then he gave an internal demo, which a lot of people found very interesting. and everybody got a little bit involved and had something to say. So a team was formed, my roadmap was cleared, and I got to work on this full time. And what we wanted to achieve is we wanted to let users express intent in natural language. So say, hey, I want to create an event, and then the chatbot walks you through this instead of having to click through a UI. So the main goal is having simple configuration flows, which also would help reduce repetitive and manual work, because sometimes an event has about 10 products and you just want to update, for example, the price. You want to make it 10% more expensive, or you want to move the end date a few days in the future, and you can just talk with this assistant and say, hey, can you do this for me, and it will do that for you instead of having to walk through the UI manually. So we want to leverage existing infrastructure. We already have an existing API in place. So this API is already used a lot in production to configure and set up and create events. So we wanted to reuse that because it also had an existing permission model. This meant we will be able to create this with minimal additional backend logic. You can just slap the AI chatbot on top of it, and it will already do most of the work for you. This means that you will have a lower maintenance cost, and you can get to your customer faster because your initial rollout will be faster as well. So you can just chat in natural language. User describes his intent instead of navigating the UI. So what you can see here is you see this prompt. It says list all messages or list all products. And because the assistant knows what page it's on, it already has the event ID, and it will list you all available products. And you can use this for other things as well. You can just ask it to delete products. And this is really valuable for like the bulk operations I mentioned earlier, because for some of these operations, we don't even have UI or UX. So this also means you can support new flows by using your existing endpoints already. So let's walk through how our system works. First, the user sends a message. This is received by our AI chatbot application. That request then gets sent to OpenAI, and it does a few iterations until it's confident that it can answer the user, and otherwise it will do an early abort and ask the user for clarification. We don't then move on to calling our internal service and send that reply to the user. How does it understand what actions are available? Because we have an existing API, we also have existing OpenAPI documentation. So we can use this documentation and store it in a vector database, and then users chatting with this assistant can use that existing documentation. So a user query gets translated in a few different queries. So if you ask, hey, can you list me all events? OpenAI makes 3 separate queries for this, and then it tries to find the relevant markdown files for this request. And these files, they're also graded with a confidence score. So you can have custom filtering and ranking options to remove context that is not relevant for this request. And one of the advantages of doing so is because you're using existing documentation, you also stay in sync with your code base. And in this context, all the documentation is available for, hey, what do I need if I want to create an event? The documentation says you need these parameters, and your request and response body will look like this. So that's really powerful, using something that already exists, adding a chatbot, and then using these features. So how do we interact with the API? Well, like I said earlier, it uses the OpenAPI documentation to construct the request. And based on this documentation, it also has the required parameters and payload. And then before we execute the request, we can do some additional safety checks, so we are in full control about the execution. And the result of this API response can then be used for future iterations, or it can be used as a response to the user. So the most important thing about this chatbot is security and control. How do we make sure it doesn't go rogue, and how do we make sure it doesn't delete all the data that we have stored in our database? So we have a few checks that we do before making a request. We control execution, so this implement checks, and we will dive into that a little bit more later. And we also enforce authentication and authorization because we already have this existing API. We can restrict this AI assistant further via the context because we control what it knows. If we don't upload something in the vector database, it doesn't know that it's available. That doesn't mean that it can still use it, because if the user instructs it and tells it that it can do something, it will try to do it. So we need to limit that as well. And we also have some rate limiting and other operational safeguards that you want to apply. So let's look at the controlled API execution. So we have a configuration class in which you can specify the methods that it will allow. So for your first rollout, you can, for example, restrict it to not support delete or put operations, which would make it really safe to just try and see what value can it have when you're trying to create new things without it being destructive. You also want to restrict it to your own API, or we want to restrict it to our own API because we don't want spamming other services. So we can say, hey, you can only talk with these endpoints, with these methods. And there's also some constraints to prevent it spamming. So sometimes it would create a plan that says, hey, execute 50 requests, and we don't want that. So we do an early abort and then prevent it from interacting with that service. So how does this actually work? So we instruct the agent to generate a structured plan, and this is basically just an HTTP request. So the body it will say, hey, I will use this method. I will try and invoke this endpoint with these query parameters and this request body. So you have full control about what it will do. So you can evaluate all the steps before letting it do this. So what we do is the plan is that for put and delete endpoints, if it wants to interact with that, we will let the user confirm this manually. And this is also, using it this way, also creates the opportunity for rollback and auditing. Because when you do a put request, you can just store the current state of the object somewhere, and then you can have support for an undo operation. And because we are already using an existing API, which has authentication and authorization, and all these tokens and permissions, we can just restrict the chatbot even further by saying, hey, you can't delete events by taking away the permission, and the executor class can also do this. So it's a double safeguard. And this will limit the blast radius in case something goes wrong which the executor does not catch. So how can you restrict the AI assistant via the context? So the context in the vector database is basically all the knowledge it operates on. If you take away some of the context, it won't know what to do. So it won't be able to help the user, and the prompt will ask for clarification. So this is not really a security way you can measure you can rely on, but you can at least use this to support the few features you want and take away knowledge about the rest that you don't want it to do. And then some rate limiting and operational safeguards. AI systems can generate actions quickly. So if it hallucinates or goes rogue, it can generate 100 requests or more. So you really want to limit this by putting some safeguards in place. And you also want to log user interaction with the assistant, because you want to know what areas is it weak on. So you need some kind of monitoring, logging, and auditing, so you can improve this thing and detect the weak points in the system. And some general lessons from working on this project I want to discuss really shortly, which are dependency injection, testability, and over-engineering. So looking at dependency injection, I think it's really powerful that we programmed it this way, because you can swap implementation. So we currently use OpenAI, but if we want to use another provider, we can just swap out the implementation and write code specific for that. and I think it generated more clean code and more testable code as well, because the testability makes it so that because of dependency injection, you can now use fakes as well. So you can actually test, is the system behaving correctly, instead of testing if some function is called. This is also refactor proof, because if you rename some method, your test will actually crash. Whilst with mocking, it might still work because a mock will just do whatever you want it to do. And it's also fast because you can fake out I/O operations, database interactions, and stuff like that. While with monkey patching, it's really good for external libraries, testing if some method gets called, and it's really convenient and quick to apply. And something about over-engineering, the system, it grew really quickly and got more complex because more features wanted to be added, and a lot of stuff. So one of the things I did early was introduce the abstraction for the LLM client. So I think that is something that you might not always want to do, because we might not even need it. We're currently using OpenAPI, and it might be fine for, because we might not ever switch to another provider. I also think that what we did well was we reused existing infrastructure. So we didn't create an MCP. A colleague of mine is actually working on this, and that is something that's really powerful, but it also creates additional code that we need to maintain. So I think it's really nice that we used our existing infrastructure for this to create some additional value while keeping the things that we need to maintain really low. And the main takeaway from over-engineering is that you should solve current workflows before creating hypothetical ones. And I guess that's all I wanted to say about this.